All right, everyone. Um, so I suppose before I begin, there's only 2 lectures left in the class. The last homework, as you all already have hopefully started on, is due this Saturday, and for part 1, and you can bring in your paper copy for part 2 on Monday, and also try to submit the part 2 scanned copy online, as I mentioned. If you have homework 9, part 2, you can submit it today. And as I mentioned last time, the syllabus for the course is going to be whatever I covered up until Monday. So today's lecture and Friday's lecture is not going to be on the final, but that also means I'm going to go really fast today and on Friday, just so that you get a taste of what you might see in those approximate numerical methods that we've been talking about, and then really the extension of all of these concepts is covered more in detail in the finite element course for those of you who might be taking it next semester. All right, any questions before I begin? Go ahead, Aaron.
Is there a practice final?
I did post a practice final maybe yesterday or this morning. And as I said, 5 questions. So take a look. Let me know if you have any questions. And this Friday, we'll have our last review session as well. So I can cover some of those problems in that Friday review session. Okay. All right. So let's jump back into this material on approximate numerical solutions that we've been talking about. What we did last time was basically we said that we want to solve these types of strong problems. So we constructed a weak form, and as you've all been hopefully doing by now in homework 9 and possibly homework 10, we saw that what we did was to approximate this. So maybe the best thing to do is to pick out the big picture. From the strong form, we went to the weak form, or from the energy form, we went to the weak form. This weak form, PVW weak form, is the one that we are approximating. We approximate that by choosing some functions for real displacement and some functions for virtual displacement. And we went through a lengthy argument of what are the conditions that need to be satisfied by these real and virtual displacement functions. Okay, so you have to be very comfortable and have a very good understanding of those concepts. What conditions do these functions have to satisfy? And then we said that a particular choice of approximation functions for real and virtual displacement can be done using this finite element method that I showed you last time. So, for example, for a one-dimensional bar, you could use these functions, which are very peculiar type of functions. The good thing about these functions is that they have what is called a compact support, meaning they are non-zero in a very small region of the entire domain. Okay, so which helps, as you know, later on when we did derivatives and when we were calculating the stiffness matrix K and the force vector F. We did all of that here. We saw that the stiffness matrix K had a very nice tridiagonal structure. And I mentioned that this structure will be preserved for any number of elements for 1D problems. But for 2D and 3D, the bandwidth, the width of this diagonal will be greater, but still you will get a very sparse stiffness matrix that would be diagonally dominant and easy to solve. Okay, so that's a good thing that we get for finite element methods, and of course these can be easily extended to 2D and 3D. I'll talk about that a little bit today. I showed you this crude MATLAB code for a finite element for a specific problem of fixed free method with exactly 4 elements. So this is not a general finite element code. This is posted on Blackboard, and hopefully you've all tried the Ritz method code and this finite element method code to get approximate solutions that look like this. All right, so today what we are going to do is to see that whether we can rearrange this finite element computation. We are going to do exactly the same computation, but we are going to rearrange that computation in a way that will be very easy to code it up in a computer to make it much more general. You can imagine that if I had 4 elements, right now I wrote this code that I showed you. This code is for 4 elements in particular. If you have more number of elements, you would have to modify the code. So that's not very convenient to do, right? If you just want to change the number of elements to get a better solution, say from 4 to 8 to 16 to 32, whatever, it's not very convenient to change the code. The idea then is that how can I change my order of computations? I still want to get to the same stiffness matrix, the same force vectors, and the same sort of idea. I want to do the same computation, but in a way that is much more systematic, so that I can automate it and put it in a computer code. So then I can tell, hey, I want 4 elements. Do the code automatically does that and gives me the result for 4 elements. If I want 400 elements, the code automatically does that and gives me the result for that. Okay, so that is done by what we call element-wise computations in finite elements. The idea is really that if I go back to the shape functions for these finite element method that we have created, if you were to plot all of these functions on the same graph, okay, if you were to plot all of those functions on the same graph, they would kind of look like this. This would be H1, 0 everywhere else. This here would be H2, H3, H4, and so on. So all I'm doing here is plotting all of the same functions on the same graph. And now we know that since we have to calculate these types of integrals in our weak form, what we are going to do is to break up any particular integral over the domain, which goes like 0 to L. Almost all my integrals go from 0 to L. What I do is I break up that integral as an integral over 0 to 1, 1 to 2, 2 to 3, and so on. So in general, I will be evaluating any integral within the length of a particular element, which I'm calling E. That element E spans from x sub E to x sub E plus 1. So these are two nodes, E and E plus 1, and I have that element number. In general, the number of nodes, if there are m elements in the domain, then there are m plus 1 nodes for a one-dimensional problem. For a 2D, 3D problem, it's slightly different, but the same ideas work there as well. So here's what we'll do. We'll break up any integral as a sum of integral over the element lengths. Is there any approximation in that? If I say integral 0 to L of whatever is equal to the sum over all of the elements from xe to xe plus 1, just calculating the same thing, is there any approximation going from here to here?
Yes.
Yes? Why do you think so?
Because let's just put the finite part to side it's like
So we've already made the approximation up here. Is that what you're saying? But from going from here to here, there is no additional approximation is what I'm saying. So if I have an integral from 0 to L, it would just be like breaking it from 0 to A and A to L. So this is what we are doing here in the element integral, and we express all of that weak form in the form of elements. Now within a particular element, I have two functions, right? If you look at any particular element, there will be exactly two functions that would be non-zero over that element. One would be h sub e, the other would be h sub e plus 1. H sub e is the one that goes from 1 down to 0, and h e sub plus 1 is going to be the one that goes from 0 to 1. Those are the only two non-zero functions within that element. Every other function in that element is 0. So using this fact, what we can do is we can approximate the real displacement as a linear sum, as a linear combination of two unknown coefficients. One is what I'm calling displacement at node 1 for element E. So if this is element E, this is node 1, this is node 2. So this, so this right here is displacement of element E at node 1, and DE2 is displacement of element E at node 2. Using those two, if I know those two values, then the function that goes from 0 to 1 and 1 to 0, if I combine that will give me an approximate value of displacement within that element. And that's the key idea of finite elements, where we approximate real displacement as n1, n2, which is written right here, times d1, d2. This is exactly the same approximation that we did with the Ritz method, with the one that I showed you before. But all I'm doing is writing it slightly differently. So U is equal to some n matrix, which we usually call the shape function matrix, times D vector, which is the degrees of freedom vector associated with that element. Okay, and this particular expression works for all types of finite element displacement based methods, where you'll be approximating displacement as some set of shape functions times some degrees of freedom. Whether it is 2D, 3D, doesn't matter. This general expression works. The exact form of the shape function matrix and the degrees of freedom vector would change a little bit, but this idea still works. And this is basically what's being said out here in words. This was the n1 function that goes from 1 to 0, and the n2 function associated with node 2 that goes from 0 to 1. And in terms of those two, you can you can approximate the real displacement, and in exactly the same manner, you can approximate the virtual displacement. Same shape functions, same n1, n2, but virtual or virtual degrees of freedom d bar on top. And as you remember, for the Ritz method, we said we don't really care about these values, right? Because at the end, we want that weak form to go to 0 for all possible u bar. So we don't really care about the values for a bar or d bars in this case. What we want to find is the real displacement at each of those nodes. So let's see how we do that. In order to substitute this approximation back into the weak form, we will also need u bar or the derivatives, because here we have u bar prime and you have u prime. So the derivative of the real displacement would just be the derivative of the shape functions. These degrees of freedom are constants. They don't depend upon x. So can you tell me what would be the derivative of this function? Would it be constant? Right? It's a linear function, so the derivative would be constant. And if you remember from last time when we talked about Ritz method, its derivative turned out to be minus 1 over LE. Right? Change in value 1 to 0 divided by the length of the element. That's the slope. That's the derivative. Right? So minus 1 over LE would be the derivative for this, plus 1 over LE would be the derivative for this. Those would be the values that would go in here. And this matrix, that is the matrix of the derivatives of the shape functions, is commonly called B matrix. And the strain within an element is just simply given by B times D. Displacement is given by N times D. Strain is given as B times D. Derivatives of shape functions times the same D. Similarly, virtual strain is just B times D bar. Okay. All right, so all we have done till now is just approximated real and virtual displacements and real and virtual strains. What we'll do next is basically substitute those approximations into the weak form that we had written out. This is the PVW weak form, where the integrals integrals are done over each element, and the result is summed over for all of the elements. And one thing to notice here is that this weak form is now a function of the real displacements for each of these elements. That's D bar, D, E, where elements go from 1 to M, and D bar. That virtual work functional was real displacement, virtual displacement. Now it is a function of all of these coefficients of real displacement, coefficient of virtual displacements. Substitute that in here, we get some expression that looks like B transpose C B. That B matrix is the one that I showed you on the previous page. For the F vector, we get n transpose B and some boundary terms that I'll talk about in a little bit. And finally, this leads me to the same type of equation that we got for the Ritz method, except that now we have a stiffness matrix that is particular to each element. So what we are getting is an element virtual displacement times stiffness, which is this all of this is the stiffness. So this is the stiffness matrix for that element times the real displacement, which is unknown, minus uh, minus F, which is given by n transpose B. Very similar to what we had for the Ritz method, except now that we are doing integrals over the element. And the good thing about doing integrals over the element is that you can put all of these integrals in a loop for I going from 1 to number of elements. Within that loop, you can evaluate these integrals and then assemble them in a much more easy way. What this long equation looks like is sort of like this in expanded form. I've written it out for you. For element 1, I get a 2 cross 2 matrix, 2 real displacements. So for example, if this is element 1, I get node 1 of element 1, node 2 of element 1, node 1 of element 2, and node 2 of element 2. So these are the virtual displacement coefficients. These are the real displacement coefficients. If you note that the displacement at node 2 of element 1 is the same as the displacement for node 1 of element 2, which is saying that D12 and D21 is exactly the same, then you can pull that out common. And when we pull that out common, effectively what that means is that I will be summing up this entry with this entry. Similarly, I'd be summing up this force column with this force column. And note, of course, that the same logic works for the real displacements also. So if you sum up all of these equations, so this first row is for element 1 plus second row for element 2, and similarly plus for all of the elements, however many elements you have, and plus the last row is for the last element. So it's not that each element itself is in equilibrium by itself. It's the sum of all of those elements that are in equilibrium with respect to each other and in totality. And at the end, we do add the boundary terms, any traction at the right end, any traction at the left end, which is these two quantities. And in addition, you can also have, in general, in finite elements, it's easy to add nodal forces at specific degrees of freedom. So you can add those degrees of freedom, nodal forces at those degrees of freedom as well. And finally, what happens is when you take out those things common, as I said, if you say that the degree of freedom at a node from the left and the right is common, you take that out common, and as I said, these two entries would be adding up together. Okay. Now, what this looks like is that there is a 2 cross 2 for each 2 cross 2 stiffness matrix for each element, and you are essentially assembling them in a big system, big stiffness matrix, and wherever the entries overlap, you add them. Okay. And hopefully you should all be able to see that this is exactly what you would get if you were to do it in a conventional way, where if you look at this 2 cross 2 and this 2 cross 2, this element stiffness matrix from element 1 and the element stiffness matrix from element 2 are being overlapped, and 1 plus 1 is what gave us 2 here, right? The same idea keeps on repeating. 2 plus 3, or 2 and 3 assembled, 3 and 4 assembled. That's how we got these 2's on the diagonal, and the 1 at 1 and 1 at n was not summed up. So we get exactly the same stiffness matrix whether you use this approach or whether you use the element-wise approach that I'm just describing right here. So finally, in the right-hand side also, you just sum up all those vectors and you end up with the exact same vector matrix vector equation. That the weak form is given by d global transpose times k d minus f equal to 0, which you want to go to 0 for all possible d bars. Okay, this is the exact same equation that you would get from the conventional, from the previous finite element approach that I told you. If you remember from last lecture, I also said that when you do get this system of equations, we set this first term a bar 0 for homogeneous boundary to enforce the homogeneous boundary condition, right? That was because we said in this problem that the first node is fixed. So I want the coefficient for h1, the real coefficient for h1 to be 0 and the virtual coefficient also for h1 to be 0. Can you tell me why should the virtual coefficient a1 bar, why should that be 0? Yes, so we know the real displacement, and therefore the virtual displacement at a point where the real displacement is known must go to 0. So that's why we want a1 bar to be 0 here. We use that logic to enforce the homogeneous essential boundary condition and the actual essential boundary condition, and came up with a reduced system of equations. In this approach, we do something very similar, and what we say is that for all of these degrees of freedom, these are the virtual coefficients and this d are the real coefficients. If I arrange them in a sequential manner, then some of those degrees of freedom in general are what we call free degrees of freedom, the ones that I want to find. These are the unknown coefficients for the for displacement, and some of those degrees of freedom may be specified. For a 1D problem, usually the specified degrees of freedom are at the end. Okay, but in general for 2D and 3D problems, that's not necessary. You can have degrees of freedom specified within the domain as well. But in general, you'll be able to break up all of your degrees of freedom going from 1 to m plus 1 nodes, all of the nodes of that bar. Some of them would be specified and some of them would be free. Okay, and once we do that, we can take that system of equations, this system of equations k d minus f, if I write that out in this form, this is k, this is d, and this is f. If I break that up into free and specified parts, so these free degrees of freedoms are the unknowns that I'm trying to solve for. The specified degrees of freedom are the displacements that are given to me. They may be 0, they may be non-zero. And in addition, I know the loads applied at the free degrees of freedom, and I don't know the reactions at the specified degrees of freedom. So the unknowns that I'm trying to solve for are the displacements at the free degrees of freedom and the reactions at the specified degrees of freedom. Okay. And at this point, I can expand the first equation of this matrix. That gives me this. I can very easily solve for dg free, that's this part, just by inverting kff, exactly like we've done last time and even for the Ritz method. And once I know this, then I can go to the second equation and I can write an expression for the reactions at the specified degrees of freedom just by expanding on the left hand side, this guys. So this will be support reactions. So this procedure of solving a finite element system of equations that you get after substituting your approximation is exactly the same as what we had for the Ritz method, or actually not for the Ritz method, but for the previous approach for the finite element that I discussed last time, and something that for those of you who took 474 with me, you've probably seen this before, or any structural analysis course that you might have taken, you should have seen this is this way to enforce free and specified degrees of freedom. Okay, so once you have the real displacements, all you need to do is to do post-processing. That is to say that if I now know that my displacement at node 1, node 2, node 3, node 4, or if I know the displacements at all these points, I can go ahead and plot that real displacement just like we've done in the MATLAB code. Take the derivatives, plot the stresses, and that's basically all that. All that is just post-processing. Okay. So the key thing that I want to emphasize here is that we are not changing the computation. We are just reordering the computation in an element-wise manner, just so that we can code it in a computer in a very convenient way, in a very systematic way. And if we do that, then it makes solving different problems with different boundary conditions, different loads, different number of elements very easy. You can use the same code. You don't have to change the code at all. All right. So, any questions on any part of this element-wise computation for the finite element method? Okay. So what I'll do is I'll talk a bit about how this methodology of Ritz method and the finite element methods can be extended to 2D and 3D problems. Okay. Keep in mind, in general, what we are trying to solve are three-dimensional structural mechanics problems, where you have some body, three-dimensional finite body. It could be as complicated as you want. You some boundary conditions, some material properties, some loading, and so on. And what you're looking for is a displacement field. That is to say that go to any point anywhere in the body, doesn't have to be at a specific node. Go to any point anywhere in the body. There are in general ux, uy, uz, or u1, u2, u3 as we have been calling them. You want to find functions, vector functions of three variables for each and every point in the body, and that's a tough problem, as we know, to solve exactly. So to do that, we will again rely on this approximate numerical method, where we will take the weak form or the principle of virtual work form of the weak form, which for 2D and 3D problems looks like this: virtual strain times real stress, that was the internal virtual work. Virtual displacement times body force, virtual displacement times tractions over the entire body, where tractions are specified. And can anybody tell me the integral over gamma d? So gamma is the boundary of the body, right? Boundary of the body is broken up into two parts, one where tractions is specified, one where displacements is specified. Where is the term for integral gamma d? It is set to 0 how? No, so gamma d is where displacement is specified. So for example, if I have this cantilever beam, if I'm applying a load here, I'm saying displacement here is 0. So the tractions won't be 0 at the point where we are specifying the real displacement, right? So what's the reason it's 0? The virtual displacement at that point is 0, right? U bar, this U bar at the place where real displacement is specified, the virtual displacement at that point is 0. That's why that term is not here. So what we'll do is we'll make approximations just like we did for 1D problem. We'll say that virtual strain will be written, or real or virtual strain will be written in this vectorial format first of all. E11, E22, E33, E, and so these are the 6 symmetric components of the strain tensor, right? Strain tensor, if you have components, is 3 cross 3, 9 components, but 6 of those are unique. So I've just listed out those 6 components of the strain tensor here, and similarly the 6 components of the stress tensor here in 3D. The purple box around here, it denotes only the components that would be required for 2D. The green ones are the ones that are required for the complete 3D problem. So we need to somehow approximate virtual strains, which means virtual displacements, and real stresses, which can be done through real displacements. So let's see how to do that. We will say that just like we did for the 1D Ritz method, displacement, real displacement, which is a vector function, so therefore u1, u2, u3, those are the unknowns. will be equal to h0x plus ai hi. This is exactly the same formula that we had for the 1D problem, right? Except now, each one of those things is a vector. H0 is not just one function. H0 is H0x component, H0y component, H0z component. And you can imagine, so for example, if I have a cantilever beam like this, I say that I'll apply an end load at the tip, and I'm saying that the fixed end here isn't really fixed, but maybe it slides down by some amount. So H0 in the vertical direction would be, let's say, 1 inch. Okay. H0 in the horizontal direction would be 0. H0 in the out of plane direction would be 0. So that's what these three components mean. In addition, for each node in the 2D or the 3D problem, I will have 3 unknown coefficients, and similarly multiplied by x, y, and z components of certain approximation function, which will be actually a function now of x, y, and z. And I'll talk about what these functions kind of look like in 2D and in 3D. But let's for now assume that we have some function. You remember what function we said? If it was a 1D problem, there's no y and z. It was just h1x, right? The type of function that we choose was x or x squared or x cubed or so on, right? In 2D and 3D, you can imagine, let's say 2D, if you have x-axis and y-axis, functions could be like x or y, could be x squared, y squared, time or xy. And so these would be the types of approximation functions that you would be choosing in this for these functions. All right, so just expanded and written out in this manner, it kind of looks like these H0 functions plus a big matrix, which is a 3 cross n matrix, because 3 components for 3D, n columns for n nodes, and you have n cross 1 vector here. Let me ask you, 3 times n multiplying a n cross 1 vector would give me a what? 3 cross 1, which is added to another 3 cross 1 to give me the approximation for my real displacements, which is a 3 cross 1 vector, right? All right. There is another neat way of rearranging these equations that will actually help us in formulating the stiffness matrix for the problem. So I'll write the exact same thing as I've written here, but in a slightly different order. I will write H1, H1, H1 here. These are all multiplying A1, A2, A3. That's the first column here. H2, H2, H2 here, multiplying A4, A5, A6, and so on. Okay. All I've done is I've rearranged this part of the matrix as this matrix right here. This matrix times this huge vector. The good thing about this is now that all my unknown coefficients are nicely arranged in a one unknown vector that I will finally solve for by again using Ka minus F. Okay, this is the exact same operation that we did even for the 1D problem, where we said that A transpose H is the same as H transpose A, right? So that's exactly what we are doing here for 2D or 3D Ritz method. And finally, we get an approximation for the real displacement, which is H0, that H0, plus n matrix. This is the big, huge n matrix that we have, times d, the unknown coefficients. So n times d, once again, that's the displacement, that's the approximation for displacement. Similarly, u bar, virtual displacement, is just n times d. There is no H0. Why? Because virtual displacement is supposed to be 0 wherever real displacement is specified, right? So that's why we don't. This is also the case that we had in the 1D Ritz method that we covered a couple of lectures ago. All right. One quick note here. This note says that it's not really easy always to find functions that satisfy these conditions that we are talking about So for example, in 2D or 3D problems, when we say that real displacement is 0 on, let's say, um, if I have this sheet of paper, um, and if I say the real displacement is 0 on parts of this edge, real displacement is some different value on parts of this edge, and somewhere in the middle, then it's difficult to construct functions in general that would satisfy those conditions, right? Um, in 1D, it's easy. I can easily pick a point. If the function goes to 0 there, then I'll create a polynomial with a root at that point. But in 2D, I have to make sure whatever function I pick satisfies the h1, first of all, that it has to be smooth. First derivative has to be square integrable, and the fact that it has to go to 0 at wherever the real displacement is specified. That's not as easy in general, but there are nice ways to enforce that. And I'll talk about that um, in this page or the next page. So what we did here is just approximated the real displacement and the virtual displacement. Now I'll plug that approximation into the expression for strains. So for strains, we know that E11 is derivative of U1 with respect to X1. Similarly, let's see. Similarly, we have the expressions for all of the other strains. And to derive these derivatives, all we need to do is to take the corresponding derivatives of the shape functions. This is the derivatives of this n matrix. Okay, just like we have H1, H1, H1 here. If I want to construct U11, for example, I would take derivative of H1 with respect to X1, H2 with respect to X1, Hn with respect to X1, and multiply with those corresponding coefficients here. That would give me strain 1, 1. Similarly, for all of the other components, all I'm doing is just constructing this big, huge matrix, which is a matrix of derivatives of the shape functions. These are partial derivatives with respect to x1, x2, and x3. And again, you should be able to note that strains are given by this big B matrix times the big unknown coefficients D vector. So B times D is strain. Similarly, virtual strain is B times D bar. Stress is D matrix times strain. So hopefully you see that this is strain. D times strain gives me stress. And at this point, I am ready to substitute these approximations into my weak form. Substitute these approximations into my weak form. I get K for 2D and 3D problems as B transpose dB d sigma, which is over the entire domain. Can you tell me what was the corresponding expression for 1D problems? C times H prime transpose, right? This is very similar. D is the material matrix, where for 1D problems we had C. This B transpose is now a vector, vertical vector. This B is a horizontal vector. So the product of all of this gives me a K stiffness matrix. Very similar to what we had for the 1D problem, but of course a little more involved. And then we can also add the contributions of the body force and the tractions. That gives me the force vector. And if I simplify that, I get to a very similar equation that we had for the 1D problem, KD minus F. So at the end of the day, you'll see that when we start off with weak forms like this, we substitute the approximations, we come to a matrix form like this, which we know how to solve. Just plug it into MATLAB, and that will give you the set of unknown vectors. As soon as you have these unknown vectors, you can go back, plug them in here. That will give you the real displacements, and you can plot them on a computer. So let me show you some examples of these functions. Let's say I have this rectangular domain, okay, and I am trying, so this is like a plane stress or a plane strain problem. Okay, so maybe for simplicity, let's take plane stress, thin sheet. So the through thickness stress is 0, but through thickness strains are not 0 in general, right? That's a plane strain problem. If I have a plane strain problem, I am applying some edge tractions all over the place. Some part of the edge is fixed in X and some part of the edge is fixed in Y and so on. Maybe, let's say, left edge is fixed for movement against X direction, but it is free to roll in the Y direction. Bottom edge is fixed to move in the Y direction, but it is free to roll in the X direction. And I'm applying some traction on the right edge, traction on the top edge, and I want to find what is the displacement of this entire sheet of plane stress material. Okay, so to do that, what we do is, just like we did for the 1D problem, we said we'll take our 1D problem and chop it up into elements, 4 elements, for example, right? Here, we'll take this entire domain, which probably looks something like this, and chop it up into elements which would either be triangular or rectangular, or in general, actually, there are some other types of approximations also. But for simplicity, let's say that we'll break it up into triangles, okay? So if you look at a particular patch of triangles within this domain, that patch of triangles might look something like this. And if you remember, in 1D, what we did was we said when we break this up into elements, that creates nodes. At each node, I will have a function that goes to the value 1 there and 0 at every other node, correct? That was the approximation function that we chose in 1D. In 2D, the approximation function would be like, for example, a patch of triangles, and at the common node of those triangles, the value of the function would be 1, and at all the surrounding nodes and all other nodes, the value of the function would be 0. So in 1D, we had like a hat-shaped function. In 2D, we have like a tent-shaped function, which goes to 1 at that particular node, goes to 0 at all the surrounding nodes, and everywhere else in the domain. That's the type of shape function that we want to use, okay, for 2D problems. For 3D problems, again, if we want to find, let's say, the displacement or a function that is similar to the finite element function, what would that look like? If I look at these 8 elements, a patch of 8 elements, so these are all cube type elements, and if you look at a patch of 8 elements, that patch might look something like this, right? At the center of the patch, there is a node, and the value of the function at that node should be 1. The value of the function at all the surrounding nodes should be 0. So you can imagine that this would be a function that can be sort of represented in color, but not really with a tent shape or hat shape or anything. Of course, 3D functions, as I said, have to be represented in color. So this would be a function that would look like, if you were to represent them in color, let's say 0 being represented with blue, 1 being represented with red, and all of the colors of the rainbow in between, then this function would look like a function that goes from blue at all around the faces and the edges, keeps on increasing to 1 at the center. That would be a 3D finite element function over a patch of elements, similar to a 2D function that looks like a tent, similar to a 1D function that looks like a hat. Okay. All right. First question, are these hat and tent, specifically this tent shape functions, are these in H1? Well, we constructed them, so they better be in H1. But what's the reason? Why are they in H1? So where are the derivatives discontinuous? Are the derivatives? So let's talk about this guy, this tent shape function, right? I have this tent shape function. Let's consider only 2 triangles here. Okay. Let's say these 2 triangles. There are derivatives in the x direction, derivatives in the y direction, and within each element you have a flat triangular face, right? So within each element, the derivative has one constant value, whether it's a derivative with respect to x or a derivative with respect to y. If we go to the neighboring triangle, that's again a face, but oriented in a different way. it has different derivatives in the x and the y directions. So the derivatives are discontinuous, right? Which is not different from our 1D problem, because even in the 1D problem, we had hat shape functions. Derivative on this side was different than derivative on this side. One was plus and one was minus. Plus 1 over LE, one minus 1 over LE. But derivatives being discontinuous is not a problem, because we know that discontinuous functions are indeed square integrable, right? So as long as the functions, these functions that we are constructing, as long as these functions are continuous, we are good with H1, okay? All right, so indeed they are in H1. And now for the other part, when I was telling you, let's say this is a plane strain or a plane stress problem with part of the edge fixed in different ways, can you think of a way that you would be able to enforce that condition here? Let's say this part of the edge, we want it to be fixed against movement in the x direction. We can simply go to those nodes and say that the x displacement of those nodes has to be 0. If I do that, then you can imagine that entire edge would go to 0, right? If this node and this node displacement in the x direction is 0, that entire edge, this entire edge has displacement equal to 0 at that point. So that's another benefit of this finite element shape function, that enforcing essential boundary conditions and enforcing homogeneous essential boundary conditions is very easy. Just using that free and specified degrees of freedom, that will enforce those conditions. And this is in contrast to some other types of methods like mesh-free methods, if some of you might have heard of those. Those mesh-free methods have supports where the function is non-zero. That does not match nicely with the boundary, and then we have to do a lot of different types of tricks to get them to match. And finally, let me give you an idea of what these functions are. For a triangular element, just like we had for the element-wise computation, if you look at each element in 1D, there are two shape functions essentially for each of those nodes. The function which goes to 1 at node 1 is 0 to 0 at node 2, and the other function that goes to 1 at this node and 0 at the other node. For a triangular element like this, we'll have three shape functions. Each of them would be functions which go to 1 at that node and 0 at the other nodes. So the blue diagram here is the one that is that represents the shape function which goes to value 1 at that node and 0 at the other two nodes. And using these three shape functions, we can approximate the displacement anywhere within this triangle. So if I know the displacement at this point, say D1, know the displacement at this point, say D2 and D3 at the other node, then I can find the displacement at this point within the element as a linear combination of the displacements at the nodes. That's the entire finite element idea, that if I have shape function n1, n2, n3 multiplied with d1, d2, d3 is the displacement at some point within the finite element. And there is a bunch of derivation here of how to find or how to construct these shape functions. Basically, you can see that these functions would be linear functions first of all for in x and y, and the linear function means that there will be three unknown coefficients, a, b, and c. And to find those three unknown coefficients, all we do is enforce these conditions, that it has to go to 1 at this point, 0 at the other two nodes, and that gives me a nice expression for the shape function associated with n alpha. Alpha could be 1 or 2 or 3. So I won't go into the detailed derivation of this. I'm sure you'll see that later on in finite elements. And the same idea extends to 2D quadrilaterals. So for example, if you have instead of a triangular element, if you have a rectangular element, now you want 4 shape functions. Each one of them would go to 1 at their node and 0 at the other nodes. And here's a question. Do you think that this would be a flat plane kind of a function? No, it would be a curved kind of a function, right? And the curve comes because you are really multiplying a one-dimensional function in x with a one-dimensional function in y. So there is a product term that looks like x times y. And so now people have done a lot of research on this already, of course, that people have tried higher order functions to try to simulate the displacement or within an element much more accurately rather than just a linear combination. A combination of linear shape functions, but again, those are things that you would see in a future course. And the same ideas that we talked about today for 1D finite elements by doing all of these computations over a particular element are of course extendable to 2D and 3D as well. And some of the common elements that you would see in 3D, for example, would be tetrahedron or a hexahedron or a prism elements. All right, so I think I'll stop here. On Friday, I'll partly do an introduction to beam theory, which is basically an actual structural mechanics theory, and give you pointers and a handout to other video lectures that are pre-recorded, but and then also kind of sum out, make a summary of what we've covered in this course. Okay? All right, so I'll see you all on Friday.